Hi, NA Physics, it's Mr. Neff. Today let's talk about impulse and the impulse momentum theorem. Look at this person pushing this box. I ask a simple question: how effective will this person be at accelerating the box? Well, the answer is it depends. It depends on a few things. It depends on how strong the person is, of course. If this person is pushing with a force like this, there'll be a certain effect. If the person is able to push with a bigger force, well then, everything else being the same, there'll be more of an effect, right? So it certainly depends on the force. The other thing depends on how long he applies the force. What do you mean by how long? Well, there's two ways to interpret that, and there's two different ways to think of the effect. I could mean how long in terms of distance. Maybe he applies a force this big until he has the box maybe moved from there over to there. Now, that's not the topic of this video because that's a work talk. That is when we say, well, how long in distance, we're talking about force, we're talking about displacement, and when you take those two things and dot them together, now you're calculating work. So anytime I ask about the effect of a force over a distance, well, that's a work problem. We know that work is equal to change in kinetic energy, and that's a talk for a different day. Now, this video is about momentum. And so this video is a similar thing. It's about the force, yes, but it's also about how much time the person pushes. If the person pushes for a little bit of time, which is hard for me to draw, right? But if he pushes for a little bit of time, then there'll be a little bit of an effect. If that same force, though, is applied for a greater time, then there'll be more of an effect. And the more time the object feels the force, the more of an effect there'll be. Similar to the way we did it for work to calculate the effect, we can take the force and multiply that by the time too. Now, this is a different kind of idea because when I multiply a vector and a scalar like this, the result will come out to be a vector. What the name that we give to that product of force and time is called impulse. Sometimes you'll see that in books symbolized by a capital J, denoted as a vector, like that. But it's that impulse that will determine how effective the force will be in changing the momentum. Now, that is putting the cart before the horse. So let's talk about that. So if I wanted a relationship between force and change in momentum, well, that's actually just the second law looked at in a little different way. Look at the top here. Second law. You're very, very familiar with that. I can say acceleration is change in velocity over time. And now I could say that that change in velocity, of course, is the final minus the initial, like you handle any change. You also see at the same time, I took that time and I moved it over to the other side, and now do you see something? Here's that force and time. Now in this last example, there was only one force. There could have been friction, there could have been other things acting, and so really the force that we're most interested in is the net force and the average net force at that. So we have this force times time, which I just got done saying is that quantity impulse. Okay. Now, if I take that mass and I distribute it through, I can get the mass times the final velocity minus the mass times the initial velocity. Now, you know by this point that mass times velocity is momentum. So this is just saying the final momentum minus the initial momentum. And so do you see something, everyone? This is the impulse momentum theorem. Why are you calling it that? Because it says that the impulse, or the effect of the force, is equal to the change in momentum. It's maybe could be called the impulse change in momentum theorem, but nobody calls it that. This is saying that the impulse and the change in momentum are going to be the same thing. Now, one neat thing that has baffled those in the past, but I don't want it to baffle you, is the units. The unit on the impulse is the unit on the force times the unit on the time. SI units are newtons and seconds. The unit on momentum will be the unit on the change in momentum. It'll be kilogram and meters per second. Now, if this is an equation, this has to be equal in every way. You notice that I have these symbols bold. That means that the direction is included there. So the direction on the impulse and the direction on the change in momentum will be the same. The magnitudes have to be the same, and the units have to be the same too. Are they? Yes, they are. And you can see that the Newton is actually a kilogram times a meter per second squared. Remember, mass and acceleration unit times a second. Those would cancel like that. And you can see that the Newton second and the kilogram meters per second are equivalent. Sometimes we just write Newton seconds whenever we're emphasizing the force and the time. Sometimes we write kilogram meters per second whenever we are emphasizing the mass and the velocity. Here's a quick example where I have a figure skater pushing off of a wall. Check it out. 46 kilogram skater is standing in front of a wall. By pushing against the wall, she propels herself backward with a velocity of 1.2 meters per second. That makes some sense too. She's going to push on the wall like this, force of skater on wall, and the wall is going to push backward on her with an equal and opposite force, force of wall on skater. Now they want to know how big is this right here. They say that after she pushes on the wall for 0.8 seconds, it's going to give her a velocity of negative 1.2. So do you see they have a force and a time, and they would like to know how much force is she pushing on the wall. So you can see force and time. This is going to be an impulse question. It's very similar to a work question, but if it was a work one, it would have said something more like she pushes for a distance of blank centimeters. Okay, so what I'd like you to do now is stop the video and give this a try and get it started again whenever you have an answer. Okay, I hope you got an answer. I hope you were successful here. We know that the impulse momentum theorem says that the impulse is equal to the change in momentum. And so I'm just looking at her right now. I'm going to actually figure out this force on her, and then I'm going to say, well, however I get, it'll be something negative because it's to the left, and then I'll just say it's that the positive version of that force will be the one that's on the wall. So right now I'm going to be mostly interested in this force right here. And how big is that force? Well, it's equal to the change in momentum divided by the time. Change in momentum is the final momentum minus the initial momentum divided by the time. Now the initial momentum will be 0 because she was stopped at the beginning of this. And so I'm just going to take her mass times her final velocity and divide it by the time. Now that's pretty straightforward. When you put the mass and the velocity in here, you end up getting a value of negative 55.2 kilogram meters per second. That's her mass and her velocity multiplied together, and then we still have to divide by the time. Whenever you go ahead and divide by the time, you're going to get a value of negative 69 newtons pushing over to the left. Now they didn't ask for the negative force, they asked for how much is she pushing on the wall. We can see in the picture that that's the positive. So this was wall on skater. Now that means that the force of skater on wall is positive 69 newtons. Okay, I've got another example. It's a little tougher than that one, but of course it would be because it's the second one. Take a look at this. A student falls freely from rest and strikes the ground. During the collision with the ground, he comes to rest in a time of 0.040 seconds. It's a bad day for the student, unfortunately. Average force exerted on him by the ground is positive 18,000 newtons. Now I know newtons are small, but that's still a lot of newtons. This student probably does get hurt. Where the upward direction is taken to be positive. And that does make sense too, because if a student is falling down, to stop, they have to be accelerated up. They have to have a force that's up, and so there's the force that they feel is the positive 18,000 newtons, which is up. It says, from what height did the student fall? So I'm thinking of this problem in two stages. There was the falling, and then there was the stopping. And we're actually going to do those stopping first, and then we're going to consider the falling. So we're going to do this in backwards chronological order. So let's say for the stopping phase, we know that they are going to go from an initial velocity of negative something, blah, 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 to a final velocity of 0. And that's going to happen in that very, very brief amount of time. And based on this and knowing that what the force is, we should very easily be able to use the impulse momentum theorem to get the initial velocity just the instant before they hit the ground. What I would like you to do is I'd like you to stop the video here, and then I'd like you to try to find that velocity just before they hit the ground. Stop the video here and come up with something on your own. Okay, you're back, and I hope that you were able to say, well, force times time is change in momentum. Change in momentum is final minus initial momentum. Now this time the final momentum is 0 because the student stopped. And so the impulse, force times time, is known, and that's going to be equal to the negative mass times initial velocity. So I'm going to say that the initial velocity is the negative force times time over the mass. And if you substitute those things in there, you will get an initial velocity of negative 11.43 meters per second. Now, they were falling down, so of course it is negative. Now, the second part of this for the for the falling is going to involve saying, okay, well, how high do you have to fall from to get up to that kind of speed? You could do it with kinematics. I'm actually going to do it with work energy theorem, just kind of going along this conservation laws trend. I think you should stop the video now. Either try to use kinematics or try to use work energy theorem to get from what height did they fall. Please go ahead and stop the video now and come up with an answer. Okay, we're back. And so, yeah, we could do it with kinematics, but I'm going to say that that the potential energy at the top and the kinetic energy at the bottom are going to be the same thing. And so I'm going to say mgh is equal to 1/2 mv squared. Now listen, I know that I have the mass of the student, so I could put it in, but personally I think that's a bit of a waste of time. So what I'm going to say is the height is going to be 1/2 the velocity squared divided by little g. And so whenever I calculate that, I see that they fell from, and by the way, that final velocity here is the same as this initial velocity there. So that's what you're going to substitute in, and I'm going to get 6.7 meters, the height that they fell. That's pretty far to fall, so you can see where that force is going to be big, and this is going to be a bad day for the student. Hey, before we wrap up today, let's talk about a scenario that a lot of people get wrong, but you're not going to get wrong. Along the lines of that last example, here we have a person that's jumping from the roof of a building, a stunt person jumping from the roof of a building, and they're not getting injured because safely out of shot, they have a large air-filled bag that they land on. And there's a million different examples of this, from different pads in sporting equipment to airbags in cars and things like that. Everything here is the same idea, in that how does something that's padded actually help? How does that stop anything? Now, sometimes people get the wrong impression, and they think that is because the impulse is actually less, but that's not really the case. So I want to take two people. Here's a person that is falling, and they're going to fall onto some kind of pad, and then we're going to have everything else the same twin person, but they're going to fall just onto the ground or something like this. So this might be the person that was in our last example. So both of these people are going to fall down, and they're both going to be stopped either by the pad or by the ground. Now, in both cases, they have the same velocity. The final velocity of both of them going to be the same size. And if I say the masses are the same, then yeah, the momentum of each of them is going to be the same. So they both have the same final momentum for the fall, and then they're both going to come to rest. So their momentum is going to go from some final amount to 0. And so both people have the same, actually I don't want to write it there, both people are going to have the same change in momentum. So both of them have the same impulse. So then why does one get hurt and the other one doesn't? Well, that impulse is going to be composed differently. The person who hits the ground with no pad, well, they're going to have a huge force to make that happen for a real small amount of time, versus the person that hits the pad is going to come to rest over a lot longer time, and so the force is going to be a lot less. and it's that smaller force that makes this safe.